1959, it was the second largest telescope in the world and remained the second largest telescope in the world until 1974. And then in the 80s and beyond, of course, many giant telescopes have been constructed. So now it's about 40th biggest telescope in the world, somewhere around there. But even though it's no longer one of the largest telescopes in the world, you can keep telescopes, older telescopes, relevant by putting new technologies on them and detecting the light in new and better ways. So we have a number of different instruments that we put on this telescope. We have the CAS spectrograph, which I'll probably talk about later when I talk about my quasar research. We have the Hamilton spectrometer, which is a high-resolution spectrograph that's been used to discover many planets around other stars. And then we have the Shane Adaptive Optics System and the Sharks infrared camera. Now, as was mentioned in the introduction, I work on instrumentation and infrared cameras and adaptive optics. So I'm going to start talking about our high-tech adaptive optics system. Adaptive optics is a technology that allows us to sharpen our images through the telescope. The Earth's atmosphere is turbulent, and it blurs your images of the stars. We've all sort of seen this effect when you see heat waves coming off of hot pavement. It makes everything shimmer and blur. Just think of that happening with the Earth's atmosphere for all the light that's coming from the stars. Blurs things. So that really a 3-meter telescope really only sees details as well as maybe a 10-inch telescope in someone's backyard because of atmospheric blurring. Well, we can use this technology called adaptive optics to unblur our images or untwinkle the stars. And this is a lovely little animation from the Gemini. Oh, no, okay, it's going to push the button on the computer itself. That shows sort of conceptually how adaptive optics works. Essentially, the light comes through the telescope, hits the primary mirror, and goes back to the back of the telescope to the adaptive optics instrument. We'll see a little cutaway version here of a very simplified schematic. And you have the light comes through the telescope. We split off the blue light, or in this case, the optical light for our system at Lick Observatory, to what's called a wavefront sensor that measures the turbulence. And then the red light, in our case, the infrared light at Lick Observatory. And then we have our aberrated wavefronts. This is essentially a representation of the turbulence. And you can see everything sort of wavy and blurry, sort of like the waves on the top of a pool if you're trying to look through the water. We then turn on the wavefront sensor, and then we put opposite turbulence on a small mirror that can change its shape at Lick Observatory up to 1,500 times a second. And then that anti-turbulence flattens out the wavefront, gives you nice sharp images through your telescope. So you get nice point-like images rather than these blurred, aberrated things that are changing every, few milliseconds. So this is great technology. How we do it is we look at a bright star, and we know what a bright star should look like if there's no turbulence. They're point sources, they're far away. And so we can look at how they're blurred, and then we use a computer to calculate what turbulence caused the blurring we see, and then put that anti-turbulence on the dipolar mirror. So, works great. The problem is there aren't bright stars everywhere you want to look, and the turbulence over there is going to be different than the turbulence over there. So, what we do is we use a laser, and we could create a fake star wherever we need one. So the laser is super cool. If the weather cooperates tonight, they're actually using the laser tonight at Lick Observatory. It is a powerful laser. We can put up to, we typically have about 10 watts of laser power. Now your typical laser pointer, like the one I'm using in my hand this evening, is about on the order of 5 milliwatts. If you have one of those nice green ones that you use for pointing out stars in the sky, it might be 10 milliwatts. So we're talking 10 watts, 1,000 times more powerful than your bright green laser pointers. So there are some safety hazards with this. We need to communicate with the FAA so that we don't illuminate any aircraft. Now, if we hit an airplane, it's not like we're going to, it's going to explode and have debris raining around the observatory, but we could blind the pilot or the air crews or passengers, and so that would be bad. You don't want your pilot to be blinded as they're coming into land at San Jose International Airport. What was our question?
Is it a visible laser?
Yes, this laser is visible. It's at 589 nanometer wavelength, which is the same colors as sodium streetlights you see here in San Jose, which unfortunately are being replaced with LEDs, but it is a yellow laser. And I also get to talk to Space Force Space Command, because some of our laser light goes right out into space, and we don't want to blind any astronauts or satellites either. But it works remarkably well. And so here's a picture of a little planetary nebula that, without adaptive optics, just looks like a big blob. You can see there's some stars there, so you get a sense of how blurred it is. And this is with the adaptive optics system on, so you can clearly see the white dwarf at the center and the planetary nebulosity around it. Now, one of the research projects I'm involved in is looking at gas giants in our own solar system and tracking the storms. So here, we have an image of Uranus, and you can see lots of storms on there, and you might actually see the faint ring around Uranus as well. And then there are a number of moons in this image. So we haven't published our results on Uranus yet, but we have published results on Neptune. So we use both Lick Observatory's telescope, and we proved the adaptive optics technology at Lick Observatory. We then put similar systems on the Keck Observatory in Hawaii. That's a 10-meter diameter telescope. And we track storms on Neptune. And back in 2017, we discovered this massive storm, an equatorial storm on Neptune. That's a big blob there, and you can see it moving in the next image. Anyway, we're monitoring this and tracking how that storm, how quickly it was moving around Neptune. So lots of images here. We've got some from Keck, Lick Observatory. They're labeled which ones were from Keck or Lick. And that storm was huge, about 8,500 kilometers in diameter. So for comparison, the Earth is, it's not as big as the Earth, but it was like 2/3 the size of the Earth. So big storm. We tracked it, and this was work done by a graduate student, mostly at UC Berkeley, Ned Moulter, and just published in 2019. And then you see this little diagram at the lower right that shows where the equatorial band is on these projections of Neptune. But this storm lasted for, quite a long time, for over 6 months. It actually lasted for almost a year. Before it dissipated. There we go. We, of course, continued observing Neptune through 2020, and we just submitted a paper. Sorry, I'm hearing an echo. A paper in February by Arandi Chavez, is another grad student at Berkeley, looking at the drift rates of storms at different latitudes of Neptune. And so the average drift rate that was measured was, I'm going to have to look this up because I don't remember the number, was, about 5 degrees per day across the face of Neptune. Talk about the white planet. Anyway, lots of pretty pictures. You can see lots of details. And of course, without the adaptive optics, it just looks like sort of one big uniform blob. And of course, I hope most of you have looked at Neptune through a small telescope and noticed its lovely blue color and things. Anyway, but adaptive optics allows us to do interesting science. So what other science do we do on Mount Hamilton? Well, we have the Automated Planet Finder. This is our second largest telescope on Mount Hamilton. 2.4 meters in diameter, and it is searching for planets around other stars. It's discovered a large number of them. And do you want to play the animation? It's not playing the animation. There we go. So it is not seeing the planets directly. It is using a technique called radial velocities, where if you have a star and a planet orbiting around it, the gravitational attraction of that planet actually causes the star to wobble a little bit. And we can use a spectrograph to measure that wobble of the star in terms of its redshift and blue shift. When things are moving towards us, the light gets shifted a little bluewards. And there we go. And when the object moves, when the star wobbles away from us, light gets shifted a little bit red. So when you look at a spectrum, when we spread the light out into its component colors, you'll see that any absorption features in the star's spectrum from, say, hydrogen or something will shift a little bit to the red, a little bit to the blue, a little bit to the... We can measure this with the Automated Planet Finder telescope. We can measure that down in our best data to a speed of about 0.5 meter per second. So I can easily walk faster than that. So we're talking strolling speed for the wobble of these planets, or the wobble of these stars. And of course, when we can measure the wobble, the bigger the wobble, that means the more massive the planet. And then the period of the wobble sort of tells you how far from the star it is. So we can measure things. So this is some data shown on the right from an actual star, 70 Virginis. It discovered a planet that was, maybe 6 times the mass of Jupiter. There we go. And of course, we've discovered other solar systems out there. So we have this HD 219134 actually has 7 planets around it. So that's so we're discovering multiple planets around single stars, and of course we're doing more and more, discovering more and more planets all the time. Now there are other ways of detecting planets. There are what's called the transit studies, so things like the Kepler Space Telescope did a remarkable job of finding planets because as the planet went in front of their star, it blocked a little bit of the light, made the star a little fainter. And so you could measure it that way. So we now know of thousands of planets around other stars. And so here's a graph showing, in the red here is how many planets have been discovered with the radial velocity technique. It takes time because you need to observe the star day after day after day and see the whole period of a planet going around its parent star. Transits, many more have been discovered because with the radial velocity technique, you look at one star at a time. With a transit, you can look at a wide field and lots of stars at the same time, so your odds of finding planets are better. The problem is that transits can sort of tell you what size the planet is, but it doesn't really tell you its mass. And so even though we've discovered planets with the transit method, you want to go and look at those same stars with the radial velocity method so you can measure the mass of that planet. And it turns out there just are not enough telescopes that can do this in the world. So we're trying to figure out how can we make our automated planet finder better so it can do more of this work. And for these newly discovered transiting planets, figure out their masses. So we have a plan, or you can see here, that one of the problems when we observe with the automated planet finder is that there's turbulence in the atmosphere. And so while we have a slit here, and we want all the light to go through that slit into our spectrograph so we can measure the radial velocity, a lot of the light spills out as the turbulence moves things around. And so we could take more data if we get more of that light to go through the slit. That means higher signal to noise in your data, which means either shorter exposures, or you can look at fainter stars. So what we plan to do is put an adaptive secondary mirror on this telescope. So this is essentially taking the adaptive optics idea that we use on the 3-meter telescope and put it on the automated planet finder. And instead of having another mirror after the primary mirror that can correct the atmospheric turbulence, change the secondary mirror. So this is tough technology. You've got to have a thin sheet of glass curved at the right shape to focus the light of the telescope. It has to have all the actuators on the back that can change the shape of that secondary mirror. But we're developing at UC Santa Cruz, my colleagues, Rachel Bowens-Rubin and Phil Hintz are working on this glass slumping technology, as they call it, to create this thin sheet of glass in the right shape. So they're well underway of figuring out that technology. Other telescopes have adaptive secondary mirrors, so we're not the first people to do this, but we're the first people to do this on a robotic telescope dedicated to observing, discovering other stars. Oh, yeah, question.
Just out of curiosity, can either of the planet-finding techniques be applied to detect binary stars, 2 stars rotating around a common center of gravity?
Yes.
Has that been done?
I'm not sure. I know that planets around binary stars have been discovered with Kepler via the transit technique. There's no reason you can't do it with, say, a spectroscopic binary star. I don't know if it's been done. It's more confusing. It's definitely more difficult because you're looking for tiny, tiny signals. So, yeah. Oh, yes. Yes.
You know, you have this wobbling in the sky, you know, there's at least one planet, but how do you know there's multiple?
So when we have a system with multiple planets, usually what we've done is we've fit the big wobble, and then we remove that. And so we discovered a planet, then we remove that wobble from the signal, and then we see another smaller wobble. And then we remove that one. And then, oh, look, there's another periodic signal we see. And so you just keep working downwards until you find, you can't pick anything else out from the noise. Okay, this is a less than perfect device. Come on. There we go. So anyway, if our modeling shows us that if we properly do an adaptive secondary mirror and use adaptive optics on the APF, you can get nearly 3 times as much light through that slit, which means you can either look at 3 times more stars in a night or look at stuff that's 3 times fainter. So it's like transforming our 1 APF telescope into 2 or maybe even 3 APF telescopes. So huge advantage. So this is what's in progress. I'm not quite sure if we have a date. I think we're still trying to raise money to finish this project, but it's well underway and very exciting if it does get implemented. Speaking of planets, we're moving back to planets in our own solar system with one of our newest telescopes, PEAS. That's Planet as Exoplanet Analog Spectrograph. It's a mouthful. This is a 1/2 meter plane wave telescope. So if you have enough money, you could buy one of these yourself. They're actually fabulous little telescopes. This was put together with all off-the-shelf parts by a postdoc at UC Santa Cruz named Emily Martin. And we have this problem. Planets in our solar system, we can see in great detail. Planets in other solar systems around other stars, we can't see in detail. So this telescope has an instrument that is designed to scramble the light from, say, Jupiter to make it sort of look more like an exoplanet around another star, so that we can start figuring out what we might be seeing with spectrographs that can actually look at the atmospheres of planets around other stars. Now, the James Webb Space Telescope, you might have noticed in just the past few days, has had press releases about planets with no atmospheres and planets that might have, other important elements like water or carbon dioxide in their atmospheres. But this is going to help us by studying planets in our own solar system as if they were planets in another solar system, and see what information we can extract as we get these new and better instruments. Now, the PEAS, essentially, it does 2 things. The light comes through the telescope, goes to an instrument, and then they split off some of the light to just take regular old pictures, like all of us are familiar with. And then the other half of the light goes to what's called an integrating sphere. So this takes all the light and essentially scrambles it, and then spits it out into a spectrograph so we can look at the spectrum. In November of 2020, it finally saw first light. It was a bitterly cold night. So this is Emily Martin and Andy Schemer with their first light information, but they took a spectra of Mars. So the spectrum actually goes into many, many fiber optics. So each one of these lines, horizontal lines on Mars, is a separate spectrum from each fiber optic. And then the sky background. So they said, yeah, they were really looking at Mars. Anyway, this telescope does not have its own dome. It lives in the basement of the 120-inch telescope. It's on a cart and we roll it out. Our undergraduate students roll it out, take their data. And so this is a regular program. We hope eventually it will have its own dome. and be remotely operable, so the students don't need to come up to the observatory. But for the time being, they get a nice scenic trip to Mount Hamilton. So now that we've talked about planets in our solar system, outside of our solar system, what might be on those planets? There might be life. So we have another instrument called Panosetti. That stands for Pulsed All Sky Near Infrared Optical Search for Extraterrestrial Intelligence. Quite a long title, but this is a program that actually started at our Nickel telescope with an optical SETI program looking for laser pulses in the optical from other civilizations that might be out there. Now, we've looked for radio signals for a long time. We've only been looking for optical signals on the order of 20, 25 years. Haven't discovered anything yet, but we keep expanding the technology, and the technology keeps getting better. So now, this dome used to house the Carnegie Dual Astrograph. That telescope was retired a couple decades ago from use, and we just put the two Panosetti telescopes here at the bottom of the slit. So these are two, 12-inch telescopes with Fresnel lenses on the front, so they have wide fields of view. And these telescopes don't move. They just look at the sky as it drifts overhead. These new technology called multi-pixel photon counters are sensitive all the way from the near ultraviolet at 300 nanometer wavelength all the way through the optical into the near infrared to the 1650 nanometer wavelengths. So there are a lot of different laser technologies out there that lays at very different wavelengths, and this system has a good chance of detecting pretty much anything at the laser wavelengths that we're familiar with using regularly. And so it's searching for these very short, transient signals. In fact, I'm very excited about this project because it shows we're sensitive. Oh, part of the plot is not showing here. Interesting. There's supposed to be a big gray box on the left-hand half of the screen, so I'm not quite sure what's weird with the display here, that you can't see it all. But things in our universe are often variable and change brightness over time. And over long time scales, minutes, hours, days, years, we have a lot of technology that's sensitive to it. When we start looking at things that change over time scales of nanoseconds to, tenth of a second, there's not a lot of technology that detects it. These multi-pixel photon counters that Shelley Wright from UC San Diego is using in her Panosetti instrument can detect nanosecond pulses. So if you're using a super fast pulse laser, her instrument will see it. So we're not just hoping to see lasers, but there are other astrophysical phenomena down here that run super fast and might be pretty bright that we may never have noticed before that her telescope will detect. So we have every chance of discovering new astrophysical phenomena as well as extraterrestrial intelligence. Pulsars can change brightness pretty quickly, up to 1,000 times a second. But as I said, there's a lot of parameter space here where there's just nothing in this plot that no one's had an instrument sensitive to before. So we have that. So as well as having the chance of detecting lasers. Yeah.
Conversely, are we sending out signals with, say, a pencil laser or some other laser to see if we get any response?
We have not purposely sent signals out with lasers that I'm aware of. Now, we certainly have lasers powerful enough that have sent signals out into space that could be detected by other civilizations. The laser we use for our laser guide star system with our adaptive optics system on the Shane telescope, not quite bright enough really for extraterrestrial civilizations to detect, but a laser that's a kilowatt of power could potentially be done. And we've shot lasers that powerful out into space many times for all sorts of different reasons. So yes, we are inadvertently sending signals out, just like we have with radio waves and television signals and everything else. So if they're out there, they might detect us and we might detect them. Anyway, the thing is this instrument is so good at detecting short, bright things that it actually detects things like, particle events in our atmosphere that create, photons and such, cosmic rays hitting the atmosphere that create little bright pieces of light. So one telescope creates a lot of confusing signals because you're like, well, did this come from our own atmosphere or did it come from space? So they have built our newest telescope on Mount Hamilton, another Panosetti, and a little tiny dome is about 6 feet in diameter with another 12-inch telescope doing the same thing, and connected them with a half-mile long fiber optic. And so these telescopes look at the same spot in the sky, and if they see a signal, they can triangulate and determine if that signal came from our own atmosphere, which we're not really interested in, or from outer space. So this is all a test program with these small test telescopes, because eventually, and we're looking to raise money to do this, we want to build full arrays of telescope that look at the whole sky all the time at 2 different sites at Lick Observatory, separated by about 0.5 or 0.6, maybe even 0.7 miles, depending on what sites we can use to do an all sky search for extraterrestrial intelligence instead of just the ones, swath of sky they can look with their stationary telescopes right now. So the next telescope I want to talk about at Lick Observatory is the nickel reflector. So this is a 40-inch diameter or 1 meter diameter telescope. It's really a workhorse telescope and where we train a lot of our undergraduate students in how to do professional astronomy. It has a direct imaging camera that takes beautiful pictures, like this picture of the Trifid Nebula that I took many, many years ago now. NIROSETI was the predecessor. The near-infrared optical search for extraterrestrial intelligence is the predecessor to the Panosetti that I just talked about. And then new last year and this year, we have 2 things. We have a wavefront sensor. Now, a wavefront sensor is that part of the adaptive optics that measures the turbulence. And then we have LAMAS, which is low latency adaptive mirror something. I've forgotten what it all stands for. Anyway, it's a new adaptive optic system for the nickel telescope. So I'll just quickly mention what's going on there. First, the wavefront sensor. As I said, the wavefront sensor is a gizmo that allows us to measure the turbulence. So also in the past, in 2022, we put in a brand new guide camera. So on the left-hand image at the bottom, you can see our guide camera, brand spanking new, much more sensitive, works so much better than the old one. And then we have a pickoff mirror that's hidden behind this lens above the camera that sends light to the little red box there. That is the wavefront sensor camera. So it's very small. And so what we're doing right now is when we're looking at the stars, we just, put a mirror in, flops in the way, blocks light to the guide camera. So you can see the wavefront sensor pickoff mirror actually blocking our guide camera field of view. In the right-hand image is that round circle. And the black blob blocking some of that circle is the pickoff mirror that's sending light from a star to the wavefront sensor. Unfortunately, I couldn't get from Micah Van Kooten, the PI of this, a picture of the wavefront sensor image itself for this talk. But she is, at the end of every night, measuring what the turbulence statistics are. So once we know the turbulence statistics, we can look at making better adaptive optic systems. But it's mostly just characterizing this. But it's new, fun hardware that we've installed at the observatory. And then we have LAMAS, and this is a project from Lawrence Livermore Labs that is going to put a fully functional adaptive optic system on the nickel telescope. This is a test program. It's not going to be permanently installed, but instead of an optical laser like we use at the Shane telescope, that's at 589 nanometers, which is yellow, it's going to use a UV laser. So we won't be able to see it with our eyes. And it's going to be super powerful. It's a 100-watt laser. So 10 times more powerful than what we use at the Shane. But it's going to be, this is a system that's designed to work super, super fast and to correct things. Because right now, adaptive optics really works best for fixing turbulence in the near infrared. It turns out that the shorter the wavelength of light, the more turbulence affects the light, and it's harder to correct. So adaptive optic systems with previous technology worked really well for correcting the turbulence that affects near-infrared light, and didn't do so well for optical light. This system is going to be optimized to do optical correction so that you could observe, say, green light and get nice images. We're working on getting the laser installed, we hope by June. We'll see. I'm working on all the paperwork for Space Force and FAA so we are allowed to use this laser safely. But we'll get beautiful images. You can see here at the upper right, whoopsie, at the upper right, this is what a short exposure image looks like through the telescope, big blob, and then the simulations of how it will work with the new adaptive optics system. You get a nice point-like source there. So as I said, lots of new technologies coming. So the last thing I'm going to talk about is my own research, my own scientific research. So we're sort of getting off the planet and adaptive optics train, but getting back onto the Shane 3-meter telescope and using our other major instrument, the CAST spectrograph, which is a medium resolution spectrograph. One of the most common things that are observed with it are supernova explosions. We have a robotic telescope at Lick Observatory called the CATE, Katzmann Automatic Imaging Telescope, that discovers supernovae, and now there are many robotic telescopes around the world that discover supernova explosions, and then we characterize them with the Shane telescope. So here's some data. This was the first data after we reopened with the pandemic and figured out remote observing with the Shane from people's own houses since they couldn't go into their offices. But we were looking at supernova 2020 JFO, which I believe is a type 2 supernova. Anyway, the line that's vertical is the supernova, and then all the horizontal lines is noise from our atmosphere or city lights here in San Jose. And of course, a lovely picture of our staff at Lick Observatory in front of the telescope that was taken right before the pandemic started. Anyway, the research I do is on quasars. And quasars are supermassive black holes at the centers of distant galaxies. And quasars are characterized by having a supermassive black hole, an accretion disk around it. Then there's usually a big dusty torus, and sometimes they have jets coming out. There's often diffuse gas further away that gets illuminated by the quasar core. Stuff gets super hot and disrupted very close to the black hole. As stuff gets spaghettified and stretched out, it generates a lot of heat, hence a lot of light. There are a lot of things, complicated things going on in there. Anyway, depending on how you view this thing depends on what you see. If you're viewing from, say up here, so you can sort of look down into the core accretion disk area, you get what are called often type 1 Seifert or type 1 AGN, active galactic nuclei. If you look from the side, through the dust torus can block stuff, so you get a different looking spectrum. Anyway, these things were discovered in the 1950s in the radio. And when they looked at these radio sources, they looked like stars in the optical component. So they were called quasi-stellar objects or quasi-stellar radio sources. We still call them QSOs today. Later on, it was discovered that they were black holes in the centers of galaxies. And it turns out that the original quasars were all identified via radio sources, but there are a lot of quasars that don't have radio components. So we don't see radio emission from them. So one of my research projects is to discover new quasars because they've been selected by optical surveys, they've been selected by radio surveys, but it turns out there are these quasars that are dust obscured. So they don't show in the optical with the same colors as the blue type 1 AGN. So this is the accretion disk and torus in the schematic here. And so blue type 1s we know a lot of, but these reddened ones that have dust in their own galaxy or dust from galaxy mergers, we're not quite sure where the dust is coming from, that makes them look redder, can block the optical light. And so we're trying to, 1, discover these red quasars, and 2, figure out, is this a phase of their evolution? What is the environment they're in? What proportion of the population of quasars these are. we're using a lot of different telescopes to figure this out. We start with the Sloan Digital Sky Survey, and we just picked the data release stripe 82, data release 7 stripe 82, because it was a confined, reasonable area that we knew we had data from radio telescopes and other telescopes that also covered the same area. And it turns out the Sloan Digital Sky Survey telescope is very effective at finding blue type 1 AGNs. It's really good at it. But obscured sources, both type 2, the ones that you're looking sort of side on with the torus, of obscuring gas, and red type 1s are missed. So they may be there, but not identified. They may be seen by Sloan, but not identified as quasars in their surveys. So we came up with a relatively unbiased way of figuring out what objects were quasars from the WISE telescope. So this is an infrared telescope that was, I forgot what year it was launched, but it's a 40 diameter telescope in space, and it maps the whole sky over and over and over again. And it came up with a total of like 563 million sources in that survey, huge number of sources. And if you look at the colors of the surface, so if you compare the light emitted at 3.4 micron wavelength and 4.6 micron wavelength versus the light emitted in 4.6 and 12 micron light, you can come up with a nice plot here that very effectively different areas are populated by different types of objects. And you can see QSO and CFIRS here are the sort of things we're looking for. And so we said, okay, if we look at things in this color regime, and so the black line is our border. So targets, the red circles are the targets we've actually observed. But if we overlay it on the plot, maybe we'll get the next slide. There we go. You can see that we have very neatly identified quasars that have the plot on the left now. The circles in red are the newly confirmed QSOs that we discovered, and the green ones are quasars that we're not 100% sure quasars yet, that we think they are, but we don't have a redshift for them. We don't know how far away they are, because unfortunately, every once in a while, you get things that confuse this, like radio stars. So that have radio emission, but are not quasars. So to get rid of the radio stars, we use Gaia. So Gaia is measuring the proper motions of like all the stars in our galaxy. It also measures a bunch of other objects, but objects that have proper motions that are measurable cannot be at cosmological distances like the quasars we're looking for. So if it has a measurable proper motion, it's a star. We reject it from our sample. A few stars are not moving significantly in Gaia. So, we get the occasional radio star contaminating our sample of things we think are quasars. So what I do with the CAST spectrograph on the Shane telescope is I take spectra of each one of our mystery objects and measure the redshift. So these are two samples, one at a redshift that's, whoopsie, not too high. Go back. Only a redshift of 0.167 now. And then we have one that's a pretty high redshift at 2.63. The highest redshift object I've measured so far with the Shane is at a redshift of about 3.5. So high redshift. And of course, now that we have all these things that are confirmed quasars based on their spectra and redshift, we now look at the radio surveys. There are two radio surveys we're using: the Very Large Array Sky Survey and the first survey, the Faint Images of the Radio Sky at 20 centimeters. So a lot of our targets don't have radio emission. They're what called radio quiet. Some of them do, like this one here is, you have the radio core, and then you have lobes at the other side. So this is a quasar, actually has jets, and the ends of the jets are very bright, making it what we call an FR2 type quasar. So as I said, we have dozens and dozens and dozens of newly discovered quasars. And here, we have various campaigns. 2019, we started off with 66 potential quasars, got redshifts for all of them. One of them turned out to be a star. 2021, we got another 34 quasar redshifts measured. We have a few quasars that have featureless spectra. These might be blazars, a special class of quasar that don't tend to have emission lines that are easy to measure, so it makes it very difficult to measure their redshifts, or they might be something else entirely. And then, you know, we're continuing. Of course, 2020, you'll see there's a big break because we had not only the pandemic, but we had a huge wildfire come through Lick Observatory, do a lot of damage. So 2020 was a pretty bad year. But these plots show, you know, the black dots are new quasars. The upper sort of magenta dots up here tend to be elliptical galaxies hosting quasar cores. The bottom magenta blob tends to be spiral type galaxies. Anyway, if you look at the redshift and how bright they are, the red dots are a newly discovered quasar. And this is only the 2019 data. I have not updated these plots to include any of our more recent data. But we're continuing on. As I said, every year we observe more. This year, I've lost all my telescope time due to snow. It's been very frustrating. We'll see. Let's hope winter is finally over. Yeah, this year was like the snowiest winter on Mount Hamilton I've ever experienced. It was something else, but it really has hampered our data collection activities. Anyway, what do? We now have to figure out which one of these are reddened quasars due to dust in their own galaxy or dust from someplace else. And some of our red quasars have very bad fits. We do modeling fits. So the top row is for two different quasars. Our bad fit of the quasar modeled quasar spectrum to what we see. If we then use a more sophisticated program called Gandalf, we can model the actual host galaxy component and subtract that out, and we get a much better fix to the galaxy. And you can see in this EB minus V is how much reddening. So here it said the reddening was 0.4. That's a lot of reddening. That's a lot of dust getting in the way of the quasar. But then once we de-redden it, you can see that the EB minus V is essentially 0. So that's great. That means that the galaxy itself, so all the obscuring dust was in the galaxy itself. Whether the dust came from something intrinsic in the galaxy with star formation or from a merging system, we don't yet know. We need to do some more research, but we've done this for like all of our quasars that had some significant reddening. And most of them, the vast majority, it's the galaxy itself, the dust in the galaxy itself that is causing the reddening. And of course, the other thing we're seeing is these red QSOs, once we de-redden them, come up in this nice brightness and magnitude, absolute magnitude relation is very, very tight. But you can see it doesn't work for the very brightest red QSOs. They don't fit very well on the rest of the line. So we're trying to figure out what's going on there, because it seems like the very most reddened QSOs tend to, at the bright end, something else is going on. And we don't know what that is yet, but I'm going to guess it's probably their emerging galaxy system. So there's extra dust and extra feeding of the black hole in this process. You could do all sorts of statistics. One of the interesting things is particularly this right-hand plot is when we look at blue QSOs, you see a nice peak here at a redshift of around 0.3 in the sample we were using. But the red QSOs, we see none at all at a redshift less than 0.1 in our sample. And there's a peak at a higher redshift. And then when you get to the higher redshift ones, we see more of them, that the red QSOs actually dominate at the high redshifts. So this implies there's something with the evolution of quasars, that something is making them more common earlier in the universe and less common now. So, like I said, lots of unknowns. We also have other statistics here with the brightness that there are two types of dust obscured quasars. So the type 2s, which I haven't really talked about much other than, you know, saying where they are, but the red type 1s. And it turns out that as you get to brighter quasars, more intrinsically bright quasars, they tend to be dominated by these dust obscured ones rather than the type 2s. And we also see that at redshift, higher redshifts, they dominate as well. So as I said, there's something going on in the evolution of these quasars. We're not quite sure what it is yet, but the more data we get, the stronger these relationships appear to be. So there really is something we think real going on there. And again, and we also looked at the radio emission. It turned out these red QSO are more likely to be radio loud than the other types of quasars. And so we've been looking at these quasars, and we have 4 different sort of types of radio sources. Ones we call faint. They're faint but compact. Compact sources, which look essentially point source-like. We have extended sources, and then we have the FR2 lights, which are sort of look like they have jets and bright lobes at the end of the radio jets. And if we look at our blue versus red QSOs, the red QSOs tend to be much more likely to be faint or compact sources versus the FR2 types. Essentially, we don't find many red ones like that at all. They're in our sample. They're just, they tend to be all blue, or virtually all of them blue. So we're starting to discover different characteristics of these, as I said, trying to tease out what is happening over the history of our universe. But first, we have to discover these things. And so that's what I'm doing with our 3-meter telescope and measuring all those red shifts. And so in closing, since I hope you've gotten a sort of feel of all the exciting things that are going on at Lick Observatory, you can come and visit us. We have public programs. Tickets for our public programs for the summer will go on sale later this month. You can go to lickobservatory.org to find out more information. Our visitor center is open Saturdays and Sundays, noon to 5 p.m. The Shane Gallery, the visitors gallery, is open every day, 10 to 5 p.m. And you could also join the Friends of Lick Observatory, and we have an online gift shop in case you can't get up to the mountain during the hours that the gift shop is open. So thank you very much.
Thank you very much, Dr. Gates. Sorry for blinding you. Thank you very much, Dr. Gates, for the excellent lecture, and sorry for blinding you with the lights coming on. So I'm going to stand here in the middle. I guess this is the mic we're going to use for questions, and most of the, partly so that people here will be able to hear you, but also we finally got the live stream working. So thank you to folks. This is so that the live stream viewers can also hear the questions. So if you have any questions for Dr. Gates, come up here and speak to the mic.
I had one question. I think I saw one of the slides that reference to the notion of creating a 3-dimensional structural map of the galaxy. Did I see that on one of the slides? And if so, if that's true, can you expound on that a bit?
So I don't think I had anything on that in my talk. Certainly Gaia is working, the Gaia telescope is working on measuring proper motions of stars. You can combine that information with radial velocities of stars and figure out where or how all the stars in our galaxy are moving. And in a sense, mapping out our galaxy that way. Now, that's a project that originally was done with the Carnegie dual astrograph and the Lick refractor back in the day, but now technologies have gotten better, so we can do it for many, many more stars. Does that address your question?
Because at least in part, there's such a map exists where it's 3-dimensional, where you can actually see where some of the positions are.
I don't know if it exists. It certainly could be programmed, but it's a massive amount of data. And so measuring, we can measure distances to stars with parallax. We can measure how they're moving. We can do all that stuff. But there are, some couple 100 billion stars in our galaxy. So even just making a map of like the nearest million stars is a lot of computational power. I'm sure it can be done. It may have been done. I don't know. But yeah.
Other questions? Can I get you to come over? I don't think the cord will go that way.
Regarding the adaptive method that you mentioned about, can you explain a bit about the resolution of those individual mirrors and then the focal length, stuff like that?
So
you said the mirror is 37 centimeters, right?
So for the automated planet finder, the adaptive secondary mirror will probably be about this big, whatever that is in centimeters. The mirrors that the Shane telescope adaptive optic system are flat mirrors, and thin glass tends to be very flexible. So you can have little pistons, glued or attached to the back that change its shape, push and pull it to change its shape. In fact, the adaptive optic system on the Shane actually uses two deformable mirrors. One uses a glass mirror that has only, 52 actuators, I think. But they can move a lot. So it does all the coarse focus, astigmatism, coma corrections. And then we have a second deformable mirror that is a MEMS device, a microelectromechanical device. It's a gold-coated mirror, actually. It's about 1 inch square, has 1,000 actuators, but they only move plus or minus a couple microns, but they use electrostatic forces. So it can move very, very fast, but it's not very much. So we call it a woofer tweeter system, sort of analogous to, speakers with low frequency and high frequency, but we're actually moving light by changing the shape of the mirror very quickly. Does that help?
Yeah.
Yeah.
Thank you. Other questions?
Are you going to be able to build any new domes on the mountain? Or I know that there was some EPA issues in the past, and I'm just curious, are you rolling telescopes out on parts?
So certainly we have sites that are already disturbed that have had buildings removed or destroyed in the SCU wildfire that we can use easily because they're already disturbed sites. Sites that have not been used for telescopes before, we do need to do environmental impact assessments and such like that. Mount Hamilton is a pretty unique ecosystem. We have rare plants, we have some uncommon animals. So we do have to be very careful of that. But there's nothing stopping us from building it. It's just an extra step in the process. But all the new telescopes we've been building and installing have all been using already disturbed sites.
Hi, so you discussed a lot about highly redshifted quasars.
Yeah.
I was wondering that James Webb recently released some pictures of extremely highly redshifted galaxies, about like 13 to 15 redshifts. So
Right.
do you think your data will be able to complement James Webb's observations, or they can build on each other?
Yeah, certainly the wonderful thing about James Webb, space telescopes and ground-based telescopes is they can do very complementary science. James Webb is very particularly designed to look at infrared wavelengths. It's a big mirror, so it can look at super faint stuff. The problem is there's only one, and there are a whole lot of astronomers that want to use it. But the data my colleagues are getting from UC Santa Cruz with those extremely high redshift galaxies is really helping us understand the very early history of the universe. And, it's looking like those galaxies are remarkably evolved for as high redshift as they are, which is a surprise. So we're looking into that. But, at what point do they turn on and become quasars? When do the massive black holes at their cores become, active? And so that we see emission from that. So there's a whole lot going on. And, it's just expanding what we can do. And we hope that we'll be able to mesh all the data sets and really understand galaxy and quasar evolution from the very earliest times of our universe.
Okay, any more questions? Oh, one more in the back there. We'll see if the cord will go that far. You might have to get up.
When you're looking at the quasar, do you happen to notice a gravitational lensing because of the distance so high and the galaxies in between?
So none of the quasars we're looking at are gravitationally lensed. There are a few out there that people study, but the ones we're discovering have not been lensed quasars yet. Doesn't mean we won't find any, but all of them so far have been unlensed systems.
Any more questions? Oh, I see one more here.
So I'm just curious, you have telescopes set up in one of the most light polluted places in the world, and how well are you able to mitigate that?
So mitigation is a couple different things we do. One is we try to work with the city planning commissions, et cetera, so that they use appropriate lighting to preserve the sky we have. There's been a lot of problems with electronic billboards and cities not wanting to necessarily adopt the standards that the International Dark Sky Association recommends for appropriate lighting. So that's one of the things we do. The other thing we do is that Lick Observatory has changed our focus. We now focus much more on developing new technologies and new techniques because we're a lower altitude facility, which means there's more air and it's easier to think at night when you're trying to figure out new difficult technologies. We're also close to San Jose and the University of California, Berkeley and Santa Cruz, and we also have shops at UCLA. So we have this huge brain trust in the reasonably local area to help us build new innovative technologies for doing new science. The other thing we've done is we've changed what science we do. We have shifted to doing more infrared work because the infrared sky is not affected by the city lights in San Jose, or we've changed to doing survey work for brighter targets. Like when we look for planets around other stars, with the APF, we can only look at one star at a time. We choose the brighter stars in our galaxy or ones that are already known to have planets because of transit discoveries with Kepler and other telescopes. Discovering supernova explosions, they tend to be pretty bright. So we have a robotic telescope discovering that. So we have focused our science onto more survey work of brighter targets that are not affected so much by the light pollution. So is light pollution good? No, we all want less of it, but there's plenty of science to be done, even with our less than perfect skies.
Okay. Is there another? Okay, excellent. Yeah, go for it.
Are your high-tech lasers produced here in the Valley?
So the laser we use on the 3 meter was built at Lawrence Livermore Labs. The one we're installing on the 40-inch telescope is a commercial laser, so I'm not sure where it's actually built.
So for the SETI, the optical SETI program, you were talking about trying to detect very, very short pulses of light. For some reason, probably something you guys have already thought about, but there's a telescope in Arizona, I think it is, that's a multiple 10-meter mirrors looking at TV gamma ray astronomy. And I know they're down at that really, really short time wavelength. Can you say anything about like how that technology differs from what you're doing with the Panosetti?
So detecting gamma rays is a really very, very different technology that I am not very familiar with at all. But we do know that gamma ray bursts can be very, very short. But some of them create optical afterglows that can last, seconds to minutes. So that's one of the things that some robotic telescopes, including at Lick Observatory, have looked for, is these optical afterglows from gamma ray bursts. Will there be some overlap in what SETI or the Panosetti discovers and the gamma ray bursts? It wouldn't surprise me at all, because now we're getting, that gamma rays are such high energy compared to the UV to IR that we're looking at with Panosetti, that, as I said, there's a possibility for all sorts of discoveries and maybe knowing more about these gamma ray bursts if they do happen to have very short optical properties as well.
Okay. Any other questions? Oh, one more here.
Hi. So I was just wondering, is the increasing number of satellites in the Earth's orbit causing contamination in the signals? Is it a big problem? And if yes, how are the telescopes dealing with that?
So it is definitely a problem. It hasn't been a problem so much for Lick with our regular data programs. Where it does affect us with all these extra satellites is when we're using our laser, because we have to shutter our laser if there's a satellite going through where we happen to be pointing our laser. And we don't want to blind any satellites that could be damaged. So we have a lot of laser shutdowns that are really irritating. In fact, next week, I'm going to Vandenberg Space Force Base to have a meeting with some of the people with them that, see what we can do to mitigate the problems. Certainly for telescopes like the Large Synoptic Survey Telescope, renamed the Vera Rubin Telescope, It's going to have a huge problem with all these satellite trails contaminating data. And they have people already working at ways to use software and data processing things to mitigate the problem. It's already a problem. More than half the active satellites in orbit are now from, SpaceX or from Starlink. And it's just increasing all the time. And there are other organizations that want to put up mega constellations. It's going to be quite crowded up there. And there are going to definitely be problems. So astronomers are actively working both in the US and internationally with these trying to work with the satellite owners and figure out ways to mitigate the problems. But it's a big problem. And we're working on it.
Okay, any last questions? I want to let you go at some point here. So any more questions? Okay. Thank you very much. Join me in thanking Dr. Gates. So again, thank you for coming. Please look at our website if you are not that familiar with all our activities. I think we're getting more and more things back in operation post-pandemic. So we have star parties here in town. We have out-of-town star parties. We have daytime observations with a solar telescope. We have a loaner program. We have a library over there. We have all kinds of activities. If you want to volunteer to help us with any of those things, that's awesome. If you want to take advantage of them, please do. As you go out the door, stop by the snacks, and then also please fill out the sign-in sheet back there. It helps the city to know how many people we have coming out, so we would love to see more names on there. And then also there's a survey there for quality of the event. So if you can do those two things, that would be awesome. We'd really appreciate it. And again, thank you for coming out. Thank you, Dr.